All right, welcome back to TalkTensors. We're ready to dive into another really fascinating paper today.
Absolutely. Should be a good one.
Yeah, this one is called Online Language Splatting.
Ooh, interesting title.
Yeah, and, on the surface, it sounds, well, technical.
Yeah.
But I think what they're doing here is really significant.
Okay.
So, imagine if you had AI, right? And it could understand your commands, like natural language commands in a 3D environment.
Okay, yeah.
But it could do it in real time.
Okay.
Even in environments it's never seen before.
Right.
That's kind of the holy grail, right?
Yeah, that's huge.
And so this paper it's really the first framework to kind of do that. They call it online, near real-time, open vocabulary language mapping within a 3D Gaussian splatting, SLAM system?
A mouthful.
Yeah. I think if you can imagine like a robot, right, going into your house and you say, hey, can you go grab me the red apple from the table? Even though it's never been in your house before,
Right.
It can actually understand where the table is, what a red apple is, and go grab it for you.
That's incredible.
Or, augmented reality, where you can ask questions about things in your environment and immediately, get answers back. So it's really, I think, a big leap forward.
Yeah.
And they're seeing, over 40 times the efficiency of previous methods, like the offline methods that have tried to do this.
Oh, wow.
And in many cases with better accuracy.
So really hitting all the marks then.
Yeah, so I think this is kind of a potential paradigm shift for dynamic and interactive AI.
Okay.
And so we're going to kind of go through and explain exactly how they did this.
I'm excited to hear it.
Cool.
Yeah, I mean, you touched on it earlier, but this idea of bridging the gap between how machines see the world, in terms of geometry and visuals,
Right.
and then how we as humans describe and interact through language, that's always been a big challenge in AI and robotics.
Mm-hmm.
So it's really cool to see a paper that's directly trying to tackle that. And that open vocabulary aspect is particularly exciting.
Yes.
It's not limited to just a set of objects it's been trained on. It can actually understand and map new things,
Sure.
which is really what we need for the real world.
Yeah, absolutely.
Because you never know what you're going to encounter.
Right, exactly. So, okay, let's talk about kind of the journey that led to this research.
Okay.
So this is all built on top of this idea of 3D Gaussian splatting, which, some people may be familiar with.
Mm-hmm.
It's become very popular recently because it allows you to render 3D scenes, with really high quality and very efficiently.
Right.
But the thing is, it's great at creating these 3D maps, but there's no real understanding of what those maps represent. Like, what are the objects? How do they relate to each other? And that's what we really need for human interaction.
Right. It's like having a beautiful picture, but not knowing what you're actually looking at.
Exactly. Yeah. And so there have been some previous efforts to kind of tackle this. One that comes to mind is LangSplat, and they used CLIP in LangSplat,
Right.
which is this very powerful model that connects images and text. It's what allows you to search for images on Google using language.
Yeah.
But the problem with LangSplat and some of the other approaches is they relied on this offline processing of language features.
Okay.
So imagine you have to pre-analyze every frame for minutes before you can even ask a question.
Oh, yeah.
That's not really practical for real-time applications like robotics or augmented reality, where you need to understand what's happening immediately.
Right. You need that instant feedback.
Right, exactly.
Yeah.
And so the big problem that the authors of online language splatting identified was, how do we inject this rich language understanding into a 3D map but do it online?
Okay.
Meaning, as the system's observing the world, you're also mapping language to it.
Got it.
And while still maintaining, the ability to understand new things, the open vocabulary aspect.
Yeah, it makes sense.
And so their framework is really the first to do that.
Wow. So they've completely eliminated that pre-processing step.
Right. There's no pre-generated language features or anything like that.
Now, that's a pretty big deal.
Yeah, it is.
I mean, to put that into context, think about the progress we've made with SLAM.
Right.
Simultaneous localization and mapping.
Yeah.
Like systems like MonoGS, which also uses Gaussian splatting, they've gotten really good at building these 3D maps in real time, on the fly.
Right.
But they haven't really focused on language. They're all about the geometry, the texture, how things look.
Yeah.
And then on the other hand, you have these methods like LangGS that can handle language, but they're stuck in that offline world. They rely on tools like SAM to segment objects and then CLIP to figure out what they are, but it all happens beforehand.
Right.
So they can't really deal with a truly dynamic environment
Right.
or answer a question about something they've never seen before.
Exactly. Yeah.
This new work is exciting because it's bringing those two worlds together.
It's like the best of both worlds. Yeah.
Okay.
And so to pull this off, they actually have three I think, really ingenious innovations that they introduce.
Okay, let's hear them.
So the first is real-time high-resolution CLIP embedding.
Right.
And so basically this is like the system's eyes and ears, right, that translates what it sees into a language representation.
Okay.
And it can do this unbelievably fast in just 18 milliseconds per frame.
Wow. So it's understanding what it's looking at and putting it into words almost instantly.
Exactly, yeah. And then the second innovation is this really clever two-stage online autoencoder.
All right.
So CLIP generates very detailed language descriptions, but they're also very large,
Okay.
in terms of data.
Right.
And so to do this in real time, they needed to compress it down, but without losing the ability to understand new things, right? The open vocabulary. And so this two-stage autoencoder can shrink it down significantly to just 15 dimensions.
Oh, that's a big reduction.
Yeah, it's pretty impressive. And then the final piece of this is what they call a color language disentangled optimization approach.
Okay, now that one sounds really interesting.
It is, and it's a little bit technical, but essentially the way that the system represents color and the way it represents the language understanding benefit from slightly different mathematical properties
Oh, okay.
within the 3D Gaussian representation. So by treating these separately during the optimization, they can actually get much better quality in terms of both how things look visually and the language understanding.
So it's like they're fine-tuning each part individually for the best results.
Exactly, yeah. And it's these three things working together that really enable online language splatting to pull off this breakthrough.
This makes a lot of sense. Let's dig a little deeper into that high-resolution CLIP embedding, though. You mentioned how fast it works.
Yeah.
But I'm curious about the detail. If the language map is blurry or not precise enough, the system won't be able to accurately pinpoint objects when asked about them.
You're exactly right.
So how do they achieve that level of detail in real time?
Yeah, so they use what's called a conjnext-based pixel-wise CLIP encoder.
Okay.
And that allows them to generate a very detailed description for every single pixel in the image.
Wow. Every pixel. That's impressive.
Yeah. And then on top of that, they use what's called a lightweight super resolution decoder.
Mm-hmm.
And that basically takes the initial language map and refines it.
Okay.
So it's almost like upscaling it to a higher resolution.
So they're taking a good language map and making it even better.
Exactly. Yeah. It's really a feat of engineering because, processing that much information that quickly is a challenge.
Yeah, for sure. And you mentioned earlier that maintaining that open vocabulary ability is really important.
Yes.
So how does this super resolution decoder, the SRD, help with that?
Yeah, so the way they train the SRB is really interesting.
Okay.
They train it on this huge data set of images like Coco and Omnidata.
Right.
But they don't need labels for every object.
Yeah.
So it learns general relationships between the visuals and the language,
Got it.
which it can then apply to new objects that it's never seen before.
Ah, so it's learning the underlying patterns of how we describe objects, not just memorizing specific examples.
Exactly, yeah.
That's clever.
Yeah. And the whole process, it only takes 18 milliseconds, with the SRD adding just 2 milliseconds on top of that.
Wow, that's incredibly efficient.
Yeah. And they actually show in the paper that these high-resolution maps lead to much better localization of small objects or objects that are far away,
Big sense.
and also more accurate boundaries for different semantic regions.
That makes a lot of sense. More detail means better understanding. Okay, so we've got these rich language descriptions.
Right.
But you mentioned earlier that they're very large in terms of data.
Yes.
How do they deal with that in a real-time system?
Yeah, so that's where this two-stage autoencoder comes in.
Right.
So each CLIP feature vector has 768 dimensions,
Yeah.
which is a lot to store and process for every point in the scene.
Yeah, that would definitely slow things down.
Yeah, so the first stage is what they call a generalized language compressor.
Mhm.
And it's actually a pretty simple neural network, an MLP-based autoencoder.
Okay.
And it's trained on a large data set, something like Coco, and it reduces the dimensionality down to 32.
Okay, so that's a pretty significant reduction already.
Yeah, and it's kind of like a general purpose compression, you know?
Got it.
It captures the core information.
Now, why not compress it down even further at this stage? Why stop at 32 dimensions?
That's a good question, and it's because they don't want to lose the nuance, right?
Right.
If you compress it too much, you might lose the ability to understand those new objects.
Like that open vocabulary aspect.
Exactly. And that's where the second stage comes in, the online learn autoencoder.
OLAE.
Yeah. And this one takes it from 32 down to 15.
Wow, okay.
But it does it in a way that adapts to the specific scene.
So it's not just blindly compressing, it's taking into account the context of what it's seeing.
Exactly, yeah. So it starts off using data from the initial keyframes of the environment.
Okay.
But then as the system moves through the scene, it updates its compression parameters.
Interesting.
And it learns what features are most important to represent the language in that environment.
So it's constantly learning and refining its compression strategy as it goes.
Exactly, yeah. And this online adaptation is important because it prevents what's called catastrophic forgetting,
Right.
where a system can forget what it learned previously as it learns new things.
That makes sense. So it's this combination of general compression and scene-specific learning that allows them to achieve such a large data reduction.
Right, and still understand a wide range of language.
Really clever.
Mm.
Okay, so we've talked about the high-resolution embedding and the compression, which are both crucial.
Yeah.
Now let's talk about that color language disentangled optimization. I'm still a little fuzzy on how that works.
Yeah, no, it's definitely one of the more technical aspects of the paper. So in the past, people have tried to integrate language into these 3D Gaussian representations. They would basically just treat the language features as extra channels.
Okay.
So within the same Gaussian parameters that are used to represent the color and the geometry.
I see. So everything was kind of lumped together.
Exactly, yeah. But the authors of this paper, they noticed that the optimal way to represent visual appearance, like the color, isn't necessarily the same as the optimal way to represent the meaning, the semantics.
That's interesting. So you're saying color and language might need different kinds of 3D representations.
Yeah, like, for example, regions that have similar semantic meaning, they might benefit from having larger Gaussians, kind of more spread out.
Okay.
Whereas to get the color right, you often need smaller, more localized Gaussians.
That makes sense.
Yeah.
So by separating them, you can fine-tune each representation more effectively.
Exactly. And so what they do is they actually have separate sets of parameters for the color and the language. But they share the underlying 3D position of the Gaussians.
So they have the same location in space, but different characteristics.
Right. And the specific parameters that are separate are opacity, scale, and rotation.
Okay.
And by doing that, when the system is learning from, say, a language-based loss, it mainly updates those language parameters.
Got it.
And the same thing for the color.
So the learning process is more focused and targeted.
Exactly, yeah. And it prevents the optimization of one from messing up the other.
That's clever. It's like giving each modality its own space to learn and grow.
Yeah, exactly. And they actually even had to add like a specific loss term to make sure the language Gaussians didn't get like unrealistically large.
Interesting. A little bit of a balancing act then.
Yeah.
So they put all these innovations together, all this clever engineering.
Yeah.
How did it actually perform?
Yeah, so they tested on these standard data sets. One's called Replica, which is a synthetic data set, computer generated of indoor environments. And then TUM RGBD, which has real world indoor scenes captured with RGBD cameras.
Okay, good mix of data then. What were they specifically testing?
So one of the key tasks they looked at was text queried object localization.
Okay.
So, can you give the system a description of an object and it has to find it in the scene?
Got it. Like find the blue mug on the shelf.
Exactly, yeah. And so they compared their online method to some of the state-of-the-art offline methods like LangSplat, Feature 3DGS, and Gaussian.
So the ones we talked about earlier that require all that pre-processing.
Right, exactly. And the results, especially on that replica data set, were pretty amazing.
Oh, okay. What did they find?
Their online method actually achieved new state-of-the-art performance.
Really?
Yeah. So it was significantly better than those offline methods.
Wow, that's impressive.
Yeah, and it was something like 40 to 200 times more efficient.
That's incredible. So not only better, but way faster.
Yeah, and that's really, I think, the big story here. I mean, like, LangSplat could take minutes to process a single frame.
Right.
So it's not even close to being real time.
You can't really interact with something that slow.
Exactly. And so, this new method, it's it's almost real time.
So it's actually usable in a practical sense.
Right. And on that TOM RGBD dataset, which is the real world one, they got results that were competitive with LangSplat.
Okay, so not quite as dramatic of a difference there.
Yeah, and the authors, they kind of say that might be because real world data is just more complex.
Yeah, it's messy.
Yeah, like you have motion blur.
Right.
Things like that. And sometimes those offline methods, because they can look at the entire sequence and optimize everything together, they might have a slight advantage.
That makes sense.
But even so, the difference in speed is just so huge.
Yeah, I mean, minutes versus near real time, that's a game changer.
Yeah, it's a totally different ballgame.
Did they look at how adding this language mapping affected the actual SLAM performance? Like, did it hurt the system's ability to build the 3D map?
Yeah, that's a good question. And so what they found was it actually didn't really hurt it.
Okay.
In some cases, they actually saw slightly better performance on things like novel view rendering and camera localization compared to MonoGS, which is that SLAM system they built on top of.
They added this whole new language understanding capability without sacrificing the core functionality.
Right. And they actually also showed that they had better 3D language mapping compared to LangSplat in the online setting.
Oh, wow. So they're actually doing a better job of associating language with the 3D structure, even though they're doing it in real time.
Exactly. Yeah. And then they did these ablation studies,
Right.
which are basically, experiments to see how important each part of the system is.
Essential for understanding the contribution of each component.
Exactly, yeah. And so they showed, for example, that using that super resolution decoder,
The SRD.
yeah, it led to big improvements in localization accuracy,
Okay.
especially for those smaller objects or the ones further away.
Right, because it's providing more detailed language information.
Right, exactly. And then they also showed that the way that they do the online compression, that two-stage approach, and specifically that online learned autoencoder, that was really critical for preserving the semantic understanding, even after you compress the data so much.
It's adapting to the scene and learning the most efficient way to represent the information.
Exactly, yeah. And then they, the experiments on disentangling the color and language optimization, those showed that was really important as well.
Okay.
Not just for the language understanding, but also for how well it renders the colors, how accurate the camera tracking is, like across the board, it was better.
It seems like all those individual pieces really came together to make a big difference.
Yeah, it was a very thorough set of experiments. It really validated all the design choices that they made.
That's good science.
Yeah. And so, thinking about this work in a broader context, we're seeing this evolution in how machines understand and represent the 3D world. We've gone from these, more traditional geometric representations to neural implicit representations like NERF, and now these explicit methods like 3D Gaussian splatting.
Right. It's been a fascinating journey.
Yeah, and the natural next step is to go beyond just mapping the geometry, how things look, and really imbue these representations with semantic understanding.
Give meaning.
Yeah, and language is such a powerful way for us to interact with the world, to describe the world.
Absolutely. It's how we communicate.
Right, and so integrating that into these 3D maps is, I think, crucial.
Yeah, it's essential if we want to build AI systems that can truly understand and interact with us in the real world.
Exactly, yeah. And for a long time, the bottleneck has been just the computational cost.
Right.
It's been hard to create these rich semantic representations and do it in real time.
It's a lot of data to process.
Yeah. But this paper, it directly addresses that.
Yeah.
It shows a way to get both the understanding and the real-time performance.
It's really building on all the progress we've seen in areas like large language models and vision language models like CLAP.
Right.
They provide the foundation for this kind of open vocabulary understanding. And this research is taking that and putting it into a 3D spatial context.
Yeah, it's really cool. And I think just to kind of summarize the core advancements here,
Okay.
the big novelty is this online open vocabulary language mapping in 3D. So as it's seeing the world, it's understanding the language.
Right. No pre-processing needed.
Right. And that leads to this huge improvement in efficiency.
Orders of magnitude faster.
Yeah, like, 40x plus. And the things that really enable this are, the high resolution CLIP embedding that we talked about, the two-stage compression.
And of course, that color language disentanglement.
Yeah, that's right. And even with those improvements in speed, the accuracy is still really good.
Yeah. State of the art or very close to it.
Yeah. And so the potential applications here are just, super exciting.
Absolutely.
And you can imagine, robots that can operate in your home or in a factory or anywhere, really. And they understand natural language instructions. They can perform complex tasks.
It's like having a truly intelligent helper that can understand what you need and act accordingly.
Exactly. And then augmented reality.
Oh, yeah.
I mean, imagine being able to look at anything and instantly get information about it.
Or ask a question
Yeah.
and get an immediate, accurate response.
Right. And no pre-scanning needed.
That would change how we interact with the world around us.
Yeah. And then you can think about, digital twins, virtual environments, all of that could become much more interactive and intuitive.
Just speak to them and they understand.
Right. And then, of course, there's autonomous navigation, especially in challenging environments.
Yeah, being able to quietly and accurately understand the scene, including what the objects are, would be a huge advantage.
Exactly. So it's really, I think, opening up a whole new set of possibilities for how AI can interact with the world.
Definitely feels like a step towards that sci-fi future we've always imagined.
Yeah, for sure. So now I think it's time for our novel notions segment.
All right, let's get speculative.
Yeah. So this is where we kind of brainstorm some potential future research directions based on, what we've talked about.
I love this part.
Yeah, me too. So one thought I had was, given how efficient they are at generating these online language feature maps, do you think it would be possible to integrate some sort of predictive language modeling into this framework?
Ooh, that's interesting. So instead of just reacting to what the user says, it's actually anticipating what they might ask.
Exactly, yeah. Like, could it learn from the environment? If it sees a messy desk, it might think, oh, the user might ask about the blue pen or the stack of papers. And if it can predict those queries, it could pre-compute the language features for those areas.
So when the user does ask, it's already got the answer ready to go.
Right. Even faster response times.
Yeah.
And so, you could maybe have this lightweight language model running in parallel.
Okay.
That's informed by the spatial context, from the Gaussians.
It's almost like giving the system a little bit of common sense.
Yeah, exactly.
Yeah.
And it could really optimize the resource allocation, make the whole interaction even smoother and more proactive.
It's a cool idea. And
Yeah.
it could potentially connect with research that's already being done in anticipatory computing.
Right. That's a good point. Okay,
And-
here's another thought.
Hit me.
So they do this color language disentanglement,
Right.
where they have separate parameters for the color and language modalities, but they share the 3D position.
Yes.
What if you could use those separate parameters to do more sophisticated manipulation?
Okay, I'm intrigued.
Like, imagine you say to the robot, move the red book closer. Could the language-specific Gaussians that are associated with red book actually be used to, precisely target and grab that object? So it's not just understanding what a red book is. It's using that language information to physically interact with it.
Right, exactly. And, maybe those language Gaussians, they encode not just the identity, but also information about how you can interact with the object, like its affordances.
Like whether you can grasp it, push it, or stack something on top of it.
Exactly. So the idea is the color and language, they benefit from these different representations. Maybe those differences could be used for more precise robotic manipulation.
It's a really cool idea, and it can have huge implications for fields like robotics and affordance learning. Imagine a robot that not only understands your command to pick up the red book, but also knows, based on its language understanding, the best way to grasp it.
Right. Yeah, that would be amazing. And so, just to be clear, these are just kind of speculative ideas.
Yeah, just brainstorming here.
Yeah. But I think they kind of give you a sense of, what might be possible building on this work. Definitely.
Yeah.
It shows the potential impact this research could have. It's not just about understanding, it's about action.
Absolutely. So to wrap up our deep dive here, online language splatting, I think it's a really big step towards this, real-time language-aware 3D scene understanding.
Yeah, it tackles a fundamental challenge in AI.
Yeah, and the efficiency gains combined with the accuracy, it's really impressive.
And it opens up so many possibilities for new applications.
Yeah, it does. And so if you're interested in learning more about the technical details, seeing the full experimental results, we have a link to the paper in the description below.
Yeah, it's worth a read for anyone interested in the future of AI.
Absolutely. And so as we wrap up, I think it's really interesting to consider how quickly these research findings might actually become real world technologies.
Yeah, how soon will we see this kind of language-aware mapping in our everyday lives.
Yeah, like in robots or AR glasses, enabling that seamless interaction.
It's an exciting time to be following this field.
It really is. The future is looking pretty intelligent.
Insightful indeed.
So thanks for joining us on this deep dive into online language splatting. We'll catch you next time here on TalkTensors.
See you then.